Okay, let's get back to this. Polarization means when your negative ions, electrons, are being attracted towards the positive ion, and those electrons are somewhat present in the center of these two nuclei. Okay, this is known as polarization. And polarizing effect is basically known as that the power or the ability of this cation to attract the electrons of the anion towards itself, that is known as polarizing effect. Okay. There are some factors on which this polarization will depend. Okay. The first thing is that what is the charge and what is the size of our cation. Charge and size of positive ion. If the positive ion is smaller in size, and having more ionic charge, that will have more polarizing effect. It means that it can attract the electrons more strongly. Okay, smaller size, more ionic charge. So if we compare sodium with potassium, we know it will be sodium that is having more polarizing effect because of its smaller size. Okay, here the positive charges are same, but if we compare sodium with some magnesium, so then magnesium is going to have the more polarizing effect because it is first, of course, it is having a smaller size, but second, it is having more ionic charge. Okay, then the second factor is what is the size and the charge on the negative ion. Okay, the negative ion, if it is larger in size, its shape can become distorted more easily. Okay? Like if we have chloride ion and we have an oxide ion. Okay? The oxide ion is having more bigger size. Okay, so bigger size means that the nucleus is not having full control over all the electrons that are present in this oxide ion. Okay, while with the chlorine, the nucleus is having a little bit more controlling effect on the electrons. Okay, like they are more attractive towards the nucleus of that chloride ion. So if a sodium ion comes near to both of these two things, it will be the oxide ion whose shape can be distorted easily. Reason? Because the electrons will be more strongly attracted towards the sodium. Second, the nucleus of this oxide ion will not have that much power to hold the electrons. Okay, because the electrons are quite spread away or they are quite far away from that center nucleus. But that is not the case in the chloride ion. The nucleus of the chloride ion is having more control over the electrons because the size of the ion is quite smaller and the electrons are more attracted towards the nucleus of this chloride ion. Okay. Of course, it can become distorted, but if you are comparing these two things, oxide will become more easily the distorted shape. Okay. So negative ions, if they're having a bigger ionic size, the distortion will be easy and the polarization will be easy. Okay. And second, if they're also having the extra ionic charges or more ionic charges, it means that they're having more electrons. So those electrons will be strongly attracted towards the positive ion. I'm going to give you the summary again. Polarization means when the cation is attracting the electrons of the negative ion and the electrons are somewhat present in the center of the two nuclei. They are having kind of a covalent character. The structure won't be 100% ionic. The polarization depends entirely on the size and the charge of the ions. Smaller ionic size of the positive ion and larger ionic charge. So it means that sodium, that positive ion would be having more polarizing effect. It can distort the shape more easily. While for the anions, bigger ionic charges and bigger ionic sizes, that will be more helpful in the distortion process. Okay? And as a result, the covalent character will be more prominent. Okay, so Let's get back to the lattice point. Lattice energies are having two values, theoretical and the Born-Haber ones, or the experimental. If they are equal, it means your compound or your ions are perfectly spherical. They are having 100% ionic character. But if the values are different, then the compound would be having some covalent character. And if the values become too much different from each other, so it means there would be more covalent character. Okay. And whenever the covalent character appears in your compound, that compound will become more stronger as compared to the one that is having completely 100% ionic structure. Okay, because you would know if there are more covalent characters, means that the ions are attracting each other more strongly. Okay, and more stronger means that the values would be more exothermic. Is it clear? Like Laika, your mic is off.
Yes, I said yes.
Okay, let's go to the concept of Born-Haber cycles now. So
Okay.
lattice energy, we cannot find it directly. Okay, we always have to use some other values to find it. So it's an indirect process. And for that, we will have a Born-Haber cycle. In the Born-Haber cycle, let's start. We have an ionic compound here. Let's say it's a sodium chloride. Okay, it's solid. We will start with elements: sodium, solid, chlorine, gas. These elements will convert into atoms first. So it means here we will have the enthalpy of atomization. You can convert the positive ones first and then the negative ones. So step by step. Okay. So first sodium goes into gaseous state. The chlorine stays the same. Then in the second step, chlorine changes into gaseous atom. And here we have to use 1/2. Okay, it can be enthalpy of atomization here. If you remember, I told you Born energy, right, yesterday, and I told you that Born energy is double of the atomization. So if in the values they are not giving you enthalpy of atomization for chlorine, they might be giving you the Born energy. Okay, and keep in mind the Born energy that they will give, it will be double of the atomization. Let's say it's 200. So keep in mind that you have to take half of this Born energy value. If it is 200, take 100 for this part where chlorine is being converted into your gaseous atom. Okay, but most of the time it will be enthalpy of atomization that would be given. Then the next is ionization of the sodium, convert into sodium gaseous. This is first ionization energy. Green stays same. Okay, plus we have 1 electron because the electron that was lost from the sodium atom. So the next, now, okay, we don't have to put it here. The arrow will move down because chlorine is going to gain that electron, convert into chloride ion plus sodium ion. Okay. Why I'm showing a downward arrow? Because this is a first electron affinity. And that is always a negative value. And then from here, it will go down to this part. This is lattice energy of formation. We are making the ionic compound from the positive and the negative ions. Okay. This one is enthalpy of formation, the one that we have studied in the AS. That elements are making the ionic compound. Okay, look. In the Born-Haber cycle, the arrows that are moving upward, they are always showing the positive value. Okay, and the one that is moving downward, they are showing the negative values. Okay, that's why I have shown the electron affinity in the downward direction. Okay. Next thing is, in the questions, they will give you all the values like formation, atomization, ionization, and even electron affinity. And they would be asking you to find out the enthalpy of formation. Sorry, lattice energy of formation. Okay, means this one. A question mark is here. We will follow the same rule, the direct pathway and the indirect pathway, as we have done in the Hess's law. The main common point is this. Okay, we are starting our reaction from here. This is our direct pathway. Okay, well, all of these values are the indirect. So the equation will be delta HF, while the rest of the values, enthalpy of atomization of sodium, then enthalpy of atomization of chlorine, then ionization energy, then electron affinity, and then lattice energy. Okay, we just have to simply put the values and find out the missing term. Clear?
Yeah.
When we are drawing the Born-Haber cycle, keep in mind the state symbols are necessary, the balancing is important, and the sequence is also important. First, always convert your elements into atoms, then into ions. Okay. If you're having more than one ionization energy, then you have to write it there. More than one electron affinity, write it there. Okay. We will solve the values later, but first I will help you to draw the other Born-Haber cycle. This time we are having calcium oxide. Okay. So starting with Ca solid, O2 gas, then calcium gaseous atom, O2, still same. Calcium gaseous, O2 changes into one oxygen, so it's gaseous. Then calcium into positive, that's first ionization, plus one electron plus O gas. Okay. Then calcium changes into Ca2 positive. So two electrons overall and Og. This is IE2. Then we have to move towards oxygen. The arrow will move downward because oxygen is going to gain the one electron first. So Ca2 positive plus one electron plus O negative. This is electron affinity 1. And then it will change into another thing. Ca2 positive plus O2 negative gaseous. Why I have drawn a upward arrow? Because the second electron affinity was always the positive. So the arrow must be shown in a upward direction. Okay. And then from here, the arrow will move directly downward here to the starting point. This is our lattice energy of formation. Here, this one was enthalpy of formation, atomization of calcium, atomization of oxygen, and then the ionization. That's how we draw the Born-Haber cycle. Is it clear, Laika?
Yes.
The next is the values will always be given in the exam. Okay. Let me show you one of a random question. So this is the Born-Haber cycle of sodium chloride. Okay. The information or the equation is given here. We have rearranged this equation. So lattice energy is here on the left hand side and all the rest of the values are present here. This is our enthalpy of formation, okay, minus 411. That is here. And the rest, first is the atomization for sodium. Then we have ionization of sodium. Then the next is atomization of chlorine. And then the first electron affinity of the chlorine. And you can see that this value is in the negative, right? Because electron affinity is always in the negative. And then just simple calculation and we got our final answer, minus 787 kilojoules per mole. Lattice energy of formation will always come in the negative values. So if you are getting an answer in positive, so it means you must have done something wrong here. And then we have something. Okay, look, this one. Here we have the magnesium chloride, MgCl2. So if you are having two chlorines, keep in mind that the atomization will be double, the electron affinities will be double as well. Okay, for the two
Okay.
chlorine atoms.
Yep.
Okay, so this is your Born-Haber. Of course, we will do some questions. Wait a second. Let me get some worksheet. Okay, starting with the first question. It's again simple. The definition for the electron affinity, and you can see it's for 2 marks, right? So you need to write down that it is the enthalpy change for the formation of 1 mole of ionic compound. Oh, sorry, not ionic compound. My bad. So electron affinity. Um, Enthalpy change for formation of 1 mole of negative ion by gaining of 1 mole of electron when both the atoms and the ions in the gaseous state. Okay, that is a simple definition. Okay, look, the second question is about completing the Born-Haber cycle. We are making the magnesium chloride, so you know first what we have to write here, the chlorine atom. That would, sorry, not atom, the chlorine molecule. Okay, then in the next part, it's the same chlorine gaseous, same chlorine gaseous. Okay. But in the next one, we will write 2 electrons here and 1 electron here as well. 2 and 1. And there we will have 2 chlorine atoms. Okay, and the next one there would be 2 chlorine negative ions.
Okay.
Quite simple. And then look, our table has been given where different values are present, and we need to find out the electron affinity. Okay, so here we are not finding out the lattice energy, but another missing term, that is electron affinity. And keep in mind, this electron affinity is for 1 chlorine atom, okay, not for 2 chlorines. In the cycle, we were having 2 chlorines. So keep in mind that at the end, you have to divide your value by 2 to get it for the 1 chlorine atom. Okay. Look, we have all the values here. The atomization for magnesium, atomization of chlorine. This one would be multiplied by 2. Reason? Because you were producing 2 chlorine atoms, right? Then first
Yeah.
ionization, second ionization, simple delta HF, and this is the lattice energy. So if I'm going to write the values, it will look like this. Minus 642 equals 150 plus 121 times 2 plus 736 plus 1450 plus there would be 2 electron affinity that of course we don't have right now, and plus minus 2493. Okay. And then we just have to like simply rearrange to get the answer. Okay. At the end, the electron affinity would be divided by 2.
Okay.
Okay. I'm going to send you 2 or 3 questions as your homework. Okay. Just try to do it because it's quite simple, similar to the Hess's law. I hope so you will get it. Okay. And if you will find any
Okay.
problem in the questions, we will pose it in tomorrow's class. Any doubts, any questions from today's lecture? Like,
Yeah.
any doubts?
No.
No? Okay. And that's all for today. Love is.